Yes, so actually we are going to summarize 6 years of good collaboration, at least from collaboration perspective, and you can judge the results. So what our aim was is to make deploying applications, complex applications in the cloud more efficient and easier, like, you know, DevOps automation. Not every application, because sometimes it's easy. We wanted to focus on applications that are distributed and pretty complex, with components, microservices, deployed over virtual machines. Can I ask to start the time ticking? Thank you. With what is also important with variable resources demand, meaning that the needs for computing power, kinds of computing power, is going to differ significantly over time, requiring more from adapting. So it's reactive to changing execution context. And what was also important is to do it in such a way that there is no need to change the code, just to have some knowledge about architecture of the software and its requirements. So the key element is actually the understanding of utility function. Simply, this system is not based on rules. It's based on utility that is almost as in economy. It exists for every choice of computing power we are going to use. We want to maximize the utility as rationality. It can be pretty complex because and have multiple dimensions. Simply, maybe computing power somewhere else is cheaper, but storage is more expensive, and what is even more important, we lose some time and we have some cost of transition. So it's actually encoding in a function the goals that we give administrator when we say what we expect from the system deployment. To give you some details, over to you, Geir.
Okay, thank you, Konrad. So what we do is that we actually base this on modeling the application, modeling the infrastructure, modeling the data, and modeling the deployment options. Now, this is quite a complex task, and as you know, this will involve many different type of expertise. So what we see here is on the left-hand side, we see actually the different roles that are participating in these models. And we have created a modeling language for collecting this information in one consistent modeling language called CAML. CAML for many reasons, but at least it has 4 pokulas, as you can see here from the 4 different roles. And the idea with this CAML language is that it ends up in a constrained programming model that allows us to optimize automatically the application when it's deployed. So, yeah, I can. You can
yeah, so this is, you know, cloud agnostic language similar to Tosca that allows to declare requirements, constraints, and utility for a software as a whole and every single module. And it's simply infrastructure requirement modeling, but in a very broad meaning. Simply, we can declare that, for example, certain modules of the software need to run in European Union because of legal constraints. So it's not only technical ones, but in general, of course, it covers application modeling, components, connections, security, and so on.
Yeah, so of course, if you have a modeling background, you know that there are already good modeling languages for this. And we base this modeling language on the EMF, Eclipse Modeling Framework, and we combined a lot of specialized DSLs, domain-specific languages, in CAML in order to ensure that we have the full coverage of the possible modeling aspects. And this is sort of becoming a complex language, but it's complete. And I mean, it's coherent and complete. Now, on top of this, we have a graphical user interface based on Modelio. Some of you might know Modelio as an open source tool. And we used Modelio to build a graphical solution for designing this complex modeling language. So that you can use Modelio and then export this as the complex textual format. Then we also have at the bottom here, you can see we have something which we call the utility function generator. You can either, if you are a mathematician like myself, you can simply type in a formula for the utility function, but you can also use tools in that utility function generator to help you to establish the connections between the different dimensions of the utility. And then finally, on the top, we see that we have a dashboard showing how the application deployment progresses through the different stages. So first uploading the model checking, then the reasoning part where we find the optimal solution, and then the deployment part. And the monitoring will then be shown in a Grafana dashboard where you can see how the model or how the application behaves and what comes back. So the way it works is that we actually build this on the theory of the autonomic computing loop, which says that basically we have added a modeling step to this theory. So first we have the model to describe the application, and then we run it through our analysis, which is basically solving the optimization problem, maximizing the utility. Then we deploy the application, and also with the deployment of the application, we also deploy tools to monitor the application so that we at any time are able to know where the application is running and how it is running on those locations. And based on that, we again do a new optimization to see if there is a better option to deploy the application elsewhere. Now, we have introduced with MORPHEMIC forecasting to this optimization loop. And why do we do that? Because in the cloud, we know that things takes time. So you do the deployment at time 0, and then we have an event management system that records the measurements as they come in from the application. The measurements can be, for instance, the number of users. This is one of the features that we have, that we allow the application to send application-specific measurements. So it's not only about CPU or RAM, that is trivial. This is about what can be important for the application. So for instance, the number of users. And these measurements, like the number of users, come at irregular intervals as we go along. At one point, we detect that, ouch, our application is not deployed in the best way now. We have a constraint violation. So for instance, if your database supports 100 users, to take a number, if user number 101 signs on, then of course this crashes, or could crash. So you want to do something about that. We have a component called the metasolver detecting that, which then goes to the solver, asks for a new solution, find a new solution for me. Then the solver asks the utility generator iteratively about what is the value of this particular candidate solution. And then we have something called performance predictor to predict what is the performance of this particular suggestion. And then again, once we have done this iteration many thousand times, we have a solution which is optimal for the values that we have measured at time point 3 in this slide. Now, then we go on and we deploy this application, and then suddenly we have a new application configuration running. But now we see that time has passed, okay? So we have a lag in this deployment, which is maybe significant, okay? So the idea we had when we started MORPHEMIC, this is done in Melodic, and MORPHEMIC adds to this the ability to be proactive. And that means we are forecasting the deployment, what it will be in the future and what the context in particular will be in the future. And how do we do that? Well, we do that, remember this loop, so we do that by simply saying that instead of measuring the actual measurement at time 3, in this case, we introduce a forecaster. And we cautiously connect this forecaster with the event management system so that the forecaster will always forecast what is required, and it forecasts that for a certain period into the future. And we use this forecast instead to produce the solution. And now we are able to produce a solution for time 28, even though we are not yet at time 28. Another thing we have introduced in MORPHEMIC is what we call polymorphic adaptation. Because today you can run software on CPUs, you can run software on FPGAs, you can run software on specialized hardware. So this means that the same software component can run on a CPU, which is cheaper in the cloud typically, or you can switch to an FPGA, which is faster, but it takes time to configure and it has a higher cost. And this allows us to change the form of your component, application component, depending on your requirements and your utility. So again, we do another layer of adaptation. Not only do we decide which component is going to be running where, but we also say in what form is this component going to be executed. Okay, so this is another layer of complexity if you want. So, the different...
Yeah, so actually, what's the evolution here between melodic and MORPHEMIC? In the case of melodic, we had a camel application model that implemented this standard autonomous loop with reactive configuration and pretty constrained utility function optimization, but it was pretty unique to offer really cross-cloud deployment. With MORPHEMIC, we have self-healing event management system. We have proactive adaptation instead of just reactive. Polymorphic adaptation that, for example, also can use GPUs when reasonably priced, or CPUs if in other scenarios, and also includes this utility function modeling. About architecture, over to you, Geir, again.
Yeah, so as you can see from the previous slide, we have been on OW2, the GitHub, GitLab Forge that you have all the time. It's continuously being developed there, so you can day by day follow our progress if you want. And of course, you are free to download and test this platform at any time. The architecture is basically well, it's a distributed system, but it's also a container-based system so that we have microservices for many different aspects. And as you see here, the evolution is that already in melodic, we had all these blue boxes available. And what we have added in the MORPHEMIC project is these yellow boxes. So we have extended melodic quite significantly, but at the same time, it's extended in a way that it is like what we call a preprocessor or an outer layer. So you can still use melodic as it is. If you want reactive optimization and all of this, you can use melodic as is. But if you want one of the additional features, you can install MORPHEMIC, which also will install melodic as the inner running core for MORPHEMIC.
Yeah, so about open source strategy, actually, since melodic, we collaborate with OW2. It is OW2 project. Everything is on a GitHub. Every component is open source. The licensing may different. Most is Mozilla. Some is APL. We, as consortium members, we offer commercial support, helping with application modeling, installation, validation, maintenance, and upgrades, including SLAs. Yeah.
So the main conclusion is that it works. It actually works. Open source collaborative development across 10 different European countries, many organizations, 65 to 100 developers, depending on what we have been doing. It actually has produced results that you can use and play with. And it works better than that. I think it works to the level that you can actually use it in production if you want. It takes away one of the main issues of cloud usage, which is the lock-in. That you can achieve some kind of auto-scaling by many cloud providers, but then you have to use that cloud provider from now on and until you decide otherwise, and that will cost you a lot. to make that decision. So we have sort of solved that problem with vendor lock-in. And we also support, if you want to ask this question afterwards, yes, we do support also Kubernetes applications that are sort of standard cloud-native applications. And we do better than that because we support it on top of resources that we can provide. So in Kubernetes, they normally operate with a static resource pool, but we can actually scale this resource pool according to the need of the application. Finally.
Yes, so finally, it is open source. I'm in open source ecosystem for 25 years. The final release is ready. We are a community that is happy to help, and actually it is used in productions. There are a number of companies that do groundbreaking things based on that technology that allows them to save significant money on both computing power, but also avoiding some manual work. So if you are interested in demo, if you are interested to learn more, simply there is a cocktail party. Please feel invited to see how it works and discuss the details.